Hello, this is going to be a comparison of a piano string being struck by a hammer and then being struck or being plucked. Okay, this has been looked into before by Arthur Benad back in 1976. He said that any plucked string has its magnitude of the nth partial attenuated by 1 over n squared, while a struck string's partials are attenuated by 1 over n. We can take a look at that concept using the simulation, which will follow. Here is the model that I'm going to use for the simulation, the stiff wave equation. This is F equals ma. Here's F on this side, and here's ma on this side. This is ma, this is m right here, and here's a, the acceleration, the vertical acceleration. Tension force, elasticity force, friction force, which causes decay, and then finally the force from the hammer strike. And the force is going to be proportional to the compression of the felt taken to a power. Then the pluck situation will be the same thing, except without this hammer force term. Okay, let's go to MATLAB and run the script. Okay, we're going to look at key A2, which is number 25. And we're going to strike at 1/8 of the speaking length. I'm going to simulate for 10 milliseconds. Okay, here's the hammer strike in green. Here's the response. We're pulling up on the bridge, pulling down on the bridge. And that's it for 10 milliseconds. Here is the long-term picture of the hammer bridge force. And here's the short-term picture. You can see that there's a pull up, a pull down, and a pause where there's no slope of the string at the bridge. Another pull up, another pull down. You can see that the shape of the bridge force changes with time because of the dispersion, which is a consequence of the elasticity of the string. And that leads to inharmonicity. Okay, here's the spectrum. You can see that the first partial in blue is pretty close to the harmonic in red, which is at 110 hertz. There it is again. This is the harmonic in red dots, and this is the partial in blue. You can also see, for example, that every eighth partial is attenuated, 16th is attenuated. You can also see that the partials start to get sharp relative to the harmonics as the frequencies increase. Okay, let's go back to the PowerPoint. And now we'll look at the pluck string, which means we go back to MATLAB and continue the same script. Okay, here's the initial condition for the pluck, 0 to about 0.9 meters. You can see up here at the top, I smoothed the corner turning here a little bit so it isn't too sharp because the sharpness causes problems with the numerical solution. All right, let's let it rip. Okay, we're pulling up on the bridge. Got a little ripple in the shape because of the elasticity. Then we're pulling down only for a short time. Now we're pulling up again. So we're pulling up. Okay, here is the 10 seconds of simulation. Here is the bridge force over 4 seconds. Here's the short term. You can see pulls up and it pulls down for a short period of time, pulls up for a longer period, pulls down, pulls up. Quite different from the case for the hammer strike. Here is the two spectra. Here are the two spectra. Here's the hammer. Here's the pluck. You can see there's a lot more power in the high frequencies for the pluck. And as a consequence, the spectral centroid or tone center is much higher for the pluck. It's 753 hertz compared to 216 hertz. The tone center is the same thing as the spectral centroid, which is an average of the frequencies weighted by the strength of the frequencies. The pitch is 110 or so, 111 over here. They're both the same pitch, as you'd expect. You'd hope. Okay, let's listen to the sounds now. First is the hammer. The second was the pluck. You can see it sounds a lot different. Let's go back to the PowerPoint. Okay, here's the comparison of the bridge forces for the two cases. Here's the hammer. Here's the bridge. A lot different. Here's the spectra, the hammer and the pluck. You can see the 1 over n for the pluck doesn't seem to be taking place here. Although the 1 over n squared is not that strong either. Let's see if we go back to the beginning. Okay. Pluck string is going to be go down by 1 over n squared, and a struck is going to go down by 1 over n. You can see that doesn't seem to happen here. Okay, so there's a difference in the bridge force traces. The bridge force sounds are different, and the spectra are different. The tone center are quite different. The pitches are pretty much the same. So thanks for watching and listening.